Okay? So as we're looking at the force, vector F is our weight going straight down. W1 is the amount of weight that's pulling that thing down the ramp. W2 is the amount of weight the ramp itself has to exert. Okay, so if we look at this, alright, I've drawn in some of the angles here. This right here, between the force vector and W2, will always equal this angle right here. Okay, the angle on the incline. The reason for that is if you look at our right triangles, okay, this right here is a horizontal, and the weight of this object is always going vertically, so this will be a right angle. Okay? This is perpendicular to the ramp. Okay? So, right here, this angle is going to be complementary to this, and it's complementary to this little angle in here. So if these are both complementary to this one, then they must be equal to each other. Okay, can't have two different numbers that add with something else to give you 90. All right, so we get this angle here congruent to this angle right here. That's kind of the key to being able to do the trig then with your vectors. Okay? So that's the first thing we want to look at as we're looking at some applications of our vectors and dot products. Yeah, Sam?
I'm confused with this problem, what we're trying to find.
Well, it depends what they ask. It depends what we're given, it depends what we're asked. We did a problem with this image specifically last Friday where we knew the vector pushing down and we knew the angle, and we wanted to figure out how much weight this boat and trailer combined were. So we were looking for the magnitude of vector F here. We could say, hey, if a boat and a trailer weigh 3,000 pounds and the angle of incline is 17 degrees, how much weight are we going to have to use to pull it up the ramp?
That would be W2.
That would be W1.
Oh, how much weight?
Okay, to pull it up the ramp.
Oh, okay.
All right. So it depends what you're given, and it depends what you're trying to find. So now here's a similar one. Here we have a cart that has 200 pounds worth of stuff in it, evidently. So total, it weighs 200. So what in here is going to be the 200?
W1.
No.
W2.
Oh, W.
F.
F.
Oh.
The magnitude of F is 200, okay? How do we weigh stuff? Something's weight is the amount of gravity pulling on it, right? So that is the magnitude of vector F, 200 pounds. Now this is saying that it sits on a ramp inclined at 30 degrees, as shown in the figure. What force is required to keep the cart from rolling down the ramp? So what are we trying to find?
V. W2.
W2F.
No, V, because isn't V pushing the cart up?
Okay, V, which is going to be the opposite of W, so if we find the magnitude of W1, it's going to be the same as the magnitude of V, right?
Yeah.
Okay, W1 is the amount of force pushing the cart down the ramp. If V is supposed to counter that, keep it from rolling down, it's got to be the same magnitude. All right? So we want to find the force required to keep the cart from rolling down the ramp. That is the magnitude of V, which will equal the magnitude of W1. Okay? Now, you can draw this picture a couple of different ways. All right, here, this was our like our W2 in the previous. That was labeled W2. Okay, and you can make your right triangle either by extending that, and then this would be your W1, and we've got a right angle here. or you can look at it the top half. Either right triangle can be used. All right. The key though is getting the correct angle. All right. If we have a 30-degree angle here, this is going to be 30, or this is going to be 30. Okay. So that's our 30-degree angle.
Inside one's 60, the other one's 60.
Yeah, and the other one is 60. And by the way, don't forget what you learned back in geometry about like 30, 60, 90 right triangles. If you remember your pattern for those,
Is it like 2x?
you can use it.
2x is the 60 side?
That's the hypotenuse.
Oh, so, okay, and then x is your smallest side.
Uh-huh.
And then square root of 3 times 2
X.
over 2 times x?
No, just square root of 3 times x.
Okay.
Yeah, you got it. All right. Got it mostly. All right, so here we have 200 pounds. Let me change colors here. Okay. We have 200 pounds right here. Okay, that's the weight. All right, we want to figure out what the magnitude of W1 is. Okay, if that's 200 pounds, well, the 30, sine of 30 will equal the magnitude of W1 over 200. Okay? So sine of 30, that you can't really see. Let me get a better color for that. Sine of 30 is the magnitude of W over 200 using our right triangle trig. So what does the magnitude of W equal? Since all of you know sine of 30
Sine of 30 is 1/2.
is a half, so times 200?
100.
100. So it's going to take 100 pounds of force to keep this thing from rolling down the hill. And obviously if we want to actually move it up the hill, we have to exert more than 100 pounds of force. Okay? Yes?
Can we use, oh, we did. Never mind.
Okay?
Can you use SOHCAHTOA for this or not?
Yeah, that's what we did. Sine is opposite over hypotenuse. The hypotenuse is that 200, the opposite is the W1. Okay. All right, so that's another one, another thing that we can do here with vectors. So let's talk about work. All right? Let's talk about work. Work is a concept in physics that I want to address briefly. I will tell you, you will have a work problem that you'll have to handle. But work is done by a constant force acting along a line of motion. Okay? Now, that force, if it is exactly in the same direction as what the thing is moving, then we just multiply the force times the distance traveled, okay? Work is force times distance, all right? Work is force times distance. Now, this right here, this formula that you see, magnitude of the force times the magnitude of PQ. That PQ is what's known as our displacement vector. Okay? You can see down here in the pictures, we're moving from P to Q. Or here we're moving from P to Q. Alright? So that's our displacement vector. In this first example that we see right here, you'll notice the force is pulling in the same direction. Okay? So this is like, you know, a cart, a horse pulling a cart. All right? It's hooked up to the cart, it's walking forward, the cart is rolling forward, they're going in the same direction. All right? So we can just take the amount of force times how far it traveled and we have work. Okay? Now, we don't always have our force vector aiming in exactly the same direction as the motion. Alright, and that's what we have in this example over here. You'll notice here that we have a force at a particular angle. Okay? This would be like if you ever, pulled a wagon behind you or something like this on wheels, and here you are walking along, okay, and you've got that handle, and as you're walking along, you're not pulling it, you don't bend over all the way, so you're pulling it like this, okay? You're pulling it at an angle, so not all of your strength is pulling that thing in the direction it wants to go, okay? Some of that strength is lost, because actually, if you think about it, some of this is actually lifting up on the front of the wagon, in this case. Alright? Some of it's lifting up. The horizontal component is what's pulling it the direction you're wanting to go. Okay? So we need a different formula. We would either need to find that horizontal component and then multiply that by our displacement. But even that only works if your displacement is exactly horizontal or exactly vertical. That's the only way you can do that. If your displacement were on an angle and you're pulling at an angle, it gets a little more complicated. So that's why we have this formula up here. We have work equals the force vector dotted with our displacement vector. Okay? Question?
If you change the force and the angle of force, would your distance change or get smaller?
Well, if you change the angle of your force, I kind of get what you're saying. It's not distance. It would be like if we lifted this up higher, less of our force would be pulling it horizontally and more of it would be lifting up. Okay? That's why if you were pulling that way and someone was sitting on this, they might tip over backwards. Okay? In fact, you see little kids do this all the time. They're going to pull their friend on something, and they start to run, but they're lifting it so high, they just flip the whole thing over, and the kid falls off the back. All right? That's because their upward component is greater than the weight of the kid that's sitting on it. All right?
You've experienced this, haven't you?
Oh, I've seen this hundreds of times. All right? Pep rallies are good when they have those little scooters that people sit on, and you like pull someone on it. That happens all the time because the rope.
Have you ever been responsible?
I'm usually on the pulling end. It's not usually unintentional, but
Oh no!
so, it's a nice prank to play.
That sounds like something a
So.
sociopath would do.
Yeah, we all have a little bit of a sociopath in us, I guess. But all right. All right. Anyways, work. If we're trying to find work, we need a unit of measure. Okay. The unit of measure that we're dealing with here is, at least in English units, it's called foot-pounds. Okay? Foot-pounds. The number, now, to have foot-pounds, your distance needs to be in feet, and your force needs to be measured in pounds. Okay? Otherwise, you don't have foot-pounds. Alright? You might have yard pounds or something like that. Okay? So, now, it's in metric units, what was force measured in metrics? Newtons, okay? And we measure distance in meters. So in the metric system, our work is measured as Newton meters. Newton meters. Okay? So, it's really easy to remember. Just look at the units of measure you're using for your distance and for your force, and that tells you you're multiplying them together with a dot product. So we have Newton meters or foot pounds.
Nanograms, wait, no, wait.
Okay? So look at an example of this happening. All right, here's an example. The old style barn doors were on these sliding tracks like this. Okay, and you'd have a rope tied to the top corner of the door, and you'd pull it, and it would slide that door across to shut the door. They didn't, instead of building hinges, they just put a little sliding track on the top. Okay, so let's say that to shut the door is 12 feet wide, so you need to move that door 12 feet. So our displacement vector, we could see our displacement vector as going 12 feet to the right and 0 feet up or down. Okay, we don't want our door to move up or down. All right, so it's just moving horizontally. But here you are, you're pulling at a 60-degree angle. And it says that you're pulling with 50 pounds of force. Okay? So the magnitude of your force vector is 50 pounds. Okay? And you're pulling at this 60-degree angle. Okay? Now, couple of things here. In order to do a dot product, our vectors have to be in component form, all right? You can't do a dot product when you have a magnitude and direction, right? So we need to first of all write this vector that we're pulling the rope with in component form, all right? So PQ, we already said, is the vector 12, 0, because it's simply moving to the right 12 feet. And vector F,
You don't know that.
we need an angle in standard position. What's our direction angle?
Right now, 300.
300.
Oh.
300, because it's 60 degrees down, so that's 300 around. So we have 50 times the vector cosine of 300, sine of 300. And you ought to know what the cosine and sine of 300 are, right?
Give me a second here.
What's the cosine of 300?
1 over,
It's negative.
1/2.
1/2.
Negative 1/2,
Nice.
right?
No, you're right.
Oh,
Cosine's
1/2
positive in the
negative
fourth
root
quadrant.
3 over-
There we go. So 1/2 times 50 would be 25. And then we have a negative root 3 over 2, right? Okay. So now we multiply by a negative root 3 over 2, and we have negative 25 root 3. So now we have our force vector in component form. That's the hardest part of this. Because now to find work is the force vector dotted with the displacement vector. Okay? So, force is 25, negative 25 root 3. And our displacement is 12, 0. I'm dotting that together.
Thank God we got a 0.
And I get 25 times 12, which is,
300, 400.
wait, no, you were right, 300. Okay? So 300 plus 0. Okay?
So is that it?
So that would be 300, what's our unit of measure?
Foot pounds.
Foot pounds.
Foot pounds.
Pound.
Okay? Foot pounds. Because we were pulling it 12 feet with 50 pounds of force. Okay? Yes.
So, the, component form, the 25, negative 25 root 3, is that on the diagram? Like, does that represent, what does that represent?
That's
on
this
that?
vector right here in component form.
Oh,
If I
that's
were to
the-
look
okay.
closer at this, okay,
Oh.
let me get into here. This is 25 pounds, and this is negative 25 root 3.
Oh.
Okay?
Okay.
That's what the component form is telling us. So actually, this also kind of tells us how much stress we're putting on the track up here. 25 times root 3, 1.7 times 25.
Something.
You know, we're putting like 35 pounds or 40 pounds worth of weight on that track. Over time, that's going to wear on it. Okay? But, so you can actually see that part as well. If we're going to pull with that much force all the time, the track shouldn't just be strong enough to hold the door, it needs to be strong enough to hold some extra weight as well. Because every time we shut that door, it's going to be pulling down on it. And in fact, if you ever see an old barn with one of these tracks, most of the time you'll see on the ends, the track is sagging. Okay? It's usually sagging down because over the years of pulling it, that weight pulling down warps the track. Okay? So. Alright, so there's our work that we're trying to find. Okay? So it's kind of a neat concept there.